Have you ever just stopped and really thought about what sound even is? Well, today, that's exactly what we're going to do. We're going to build a sound from scratch, piece by piece, so we can really understand its fundamental ingredients.
It sounds like a trick question, right? I mean, one is so quiet you can barely hear it, and the other is just deafening. But what if I told you they're both built from the exact same stuff? Yep, the answer to that question is the key to understanding all sound, and we are about to unlock it.
You see, at its absolute core, every single sound you've ever heard starts with a simple vibration. When something vibrates, it basically shoves the air molecules around it, creating these invisible waves of pressure that travel to our ears. That wave is the raw material for absolutely everything we hear. So if we're building our own sound, the very first decision we have to make is how loud it's going to be. Are we making a whisper or are we making a roar? This is our first building block, volume. It feels pretty intuitive, doesn't it? But what's actually going on scientifically? What knob are we turning in the physics of that sound wave to crank the volume up or down? The answer is something called amplitude. Now, the easiest way to think about it is like a wave in the water. A tiny little pebble makes a tiny little ripple, right? That's low amplitude. But a huge boulder, that creates a massive wave, high amplitude. Sound works pretty much the same way. A more intense vibration creates a bigger, more powerful sound wave. And it's a super direct relationship. The bigger the amplitude, the more energy that wave is carrying, and the louder the sound our brain says it is. It's really that simple. More power in, more volume out. Now, we measure all this loudness in units called decibels, or dB for short, and the range our ears can handle is just incredible. It starts at 0, literally the quietest sound a human can possibly detect, and goes all the way up to a jet engine at 140 dB, which is, get this, trillions of times more intense. Mind-blowing. Now, out of all those numbers, I want you to zero in on this one, 80 decibels. It's about the same level as a vacuum cleaner. It doesn't seem crazy loud, but it's actually a really critical threshold. And this is why it matters so much. If you're exposed to any sound above 80 decibels for a long time, it can cause permanent hearing damage. So, you see, understanding amplitude isn't just a cool science lesson. It's about knowing when to protect your hearing. Our first building block, volume, has a huge real-world impact. Okay, so we've set our volume. Let's move on to our second building block. Now we get to decide if our sound is high, like a flute, or low, like a big bass drum. We're talking about pitch. I mean, we know they sound different, but why? We've already figured out they could have the exact same volume, the same amplitude, so there has to be something else going on with that wave, right? And that something else is frequency. So while amplitude was the size of the wave, you can think of frequency as the speed of the wave's vibration. It's just how many times that wave wiggles back and forth in a single second. And we measure this in a unit called hertz. And the connection here is really direct. A high-pitched whistle is making the air vibrate super fast. That's a high frequency. A deep, low-pitched drum, that comes from a much slower, lazier vibration, a low frequency. So by controlling the speed of the vibration, we get to control the pitch. Pretty cool. All right, so we've got volume and we've got pitch. But there's still something missing, isn't there? This next layer is what gives a sound its unique character, its personality. Let's talk about timbre. This is where things get really fascinating, because amplitude and frequency alone can't answer this question. If a violinist and a guitarist both play the exact same note, at the exact same loudness, we can still instantly tell them apart. How is that possible? The answer is this thing with a kind of fancy name, timbre. It's pronounced timbre. And all it really is the color or the texture of a sound. It's the reason a saxophone sounds all smooth and a trumpet sounds so brassy. Timbre is like the sound's unique fingerprint. So where does it come from? Well, timbre is all about the unique shape of the sound wave. See, a single note from an instrument isn't just one pure, clean frequency. It's actually a main frequency mixed with a whole bunch of quieter, higher frequencies called overtones. And the specific blend of those overtones is totally different for every single instrument, which is what gives each one its special sound. So we have all our building blocks: amplitude for volume, frequency for pitch, and timbre for character. Now, for our final mix, let's look at how organizing these elements creates the huge difference between what we call music and what we call noise. And believe it or not, here's the final piece of the puzzle. Music is simply sound with a pattern. The vibrations are regular, they're organized, they're predictable. Noise, on the other hand, is just chaos. The vibrations are totally irregular and random, with no pattern to be found. It's really just the difference between order and disorder. So let's do a super quick recap of our project. We started with a basic vibration. We used amplitude to give it volume, we dialed in the frequency to set its pitch, and finally, the unique waveform, with all its little overtones, gave it a distinct timbre. And just like that, we've successfully built a sound from scratch. So the next time you hear a favorite song, or an annoying car alarm, or even just the sound of a friend's voice, you'll know exactly what's going on. You'll be able to hear the volume, the pitch, and that unique timbre. So, my question for you is, what's the first sound you're going to deconstruct?